So welcome back. The break was really good, not only because we all live by coffee, but I got one excellent question, and now I'm a bit puzzled. I just sort of worked on the answer. You see there at the bottom. I was sort of a little quick, possibly, because we haven't stressed sugar that much. So someone asked me, CumSum 3, when you're going off calling CumSum, what actually is being called? If you really wanted to know, it's sort of somewhere. It's really, so I'll just keep talking. I mean, it's really C++ code. So that gets dispatched. So that would be code from this file, if you really wanted to know. So the looping happens at C++, just saying that when we call this here, this now is a C++ function. But then a related question arose, so, okay, so that's really a C++ function you guys wrote that comes with Rcpp. What would happen if we actually called the R function? Because remember, I just showed you guys that how to call an R function. So then in the break right now, I just wrote CumSum 4. And now CumSum 4, same interface, so it does the same thing as the other guys. In comes numeric vector x, but then I instantiate myself a C++ action to an R function, CumSum. CumSum is in stats or in base. It's in base. So I could be even more explicit. I think that still runs to really make sure we're calling that from. Let me just make sure that it works here too. Compile. Nope. That didn't work. So hold on, because there is no such thing as base. Is there package base? Base CumSum. That's weird. Okay, let's forget that for a second. But that's just what function does. I mean, it resolves that string and gets us the R function back. So that's an R function. Then I just wanted to see what happens, and so let's just compare. Let's just take a really long vector from 1 to 1,000,000 elements, multiply it with 1, 0 to really get a numeric vector rather than have the implicit copy. And then I'm first making sure that CumSum 1 to 4 really give me the same result. Yes, that's true. And then, and that's why it's a really good question, I get a super counterintuitive result, because I was expecting CumSum 1 to 3 to be sort of, relatively quick and opening a gap to CumSum 4. Then I wasn't quite sure what to expect between CumSum 1, 2, and 3. Remember, CumSum 1 was the ones where we, as pedestrian C programmers, possibly worse than library implementers, loop over all elements. CumSum 2, we're actually making use of a facility given to us by expert C++ library writers. We're using accumulate from the standard library, so possibly faster. That works out. Then CumSum 3 is ours in Sugar. There's a fair amount of tuning in there. We're doing tricks to enroll loops in parallel, turns out. That one's actually slower. And here's the real hammer. It's the slowest of the bunch. And I'm a bit puzzled by that. And the weirdest thing is then, just as a counterexample, where I was expecting to see the overhead of the function call happening, none of that. It's actually the fastest of the bunch. But sort of then thinking about it a little bit, I think what happens is that in R itself, CumSum is sort of probably just about the cheapest thing that you can do on a vector. I mean, it just literally sums over the damn thing and doesn't do anything else. And there's a primitive in there. And this may be just the least overhead thing that you can have. And in this particular case, there's actually no work being done, so the comparison is a bit weird. The R function actually doesn't exhibit a cost. If we did this looped and called a function multiple times, then I guess the overhead of calling a function would amortize, but doesn't. So that was one question, answering one question that came up in the break. And then it's really good that I had the break, because I did what you should never do when you're giving a presentation. I just changed my slides, because in coming from sort of 6 blocks of about an hour and a half to using, is that what I had? No, yeah, something like that. To just 2 times an hour and a half, I chopped too much. So I let go of this section that I meant to get to before we got to the gallery. So I'm just rewinding a little. This is just 3-4 slides. Now formally introducing you to our good friends eval-CPP, CPP function, and source-CPP, because otherwise it would get skipped. So those are 3 things in what we're calling Rcpp attributes. Rcpp attributes has its own really well-written vignette. It's something that JJ from RStudio contributed when we were 2 or 3 years in with Rcpp, and it makes it a lot better. So the simplest of the 3 functions just evaluates a string as a blob of C++. So 2 plus 2 is, remember what I told you, as this in this sort of brute mini introduction to C++, doesn't have a semicolon at the end, doesn't do types and whatever, but you can ask yourself sort of what is C++, and there's enough stuff that we put around it behind the scenes so that it evaluates, and we usually use this, you know, if you get called, you know, you come back to the conference, you're super enthusiastic, you talk to your colleagues about it, Rcpp is the bee's knees, and so they set it up on their computer and they have trouble. So with eval-CPP, you can always check that your compiler is sort of right. If you get 2 plus 2, if you get 4 back, or similar for other simple expressions, and the result comes back, then your system is set up and you can build. If you get error messages, it just means something's not quite right. Again, RStudio is quite helpful there in catching some error messages if on Windows your path is wrong, whatever. And with eval-CPP, you can do other things too. This is the equivalent to, what is it, dot machine, dollar, double max or sort of something. It's just basically on a 64-bit machine, the largest floating point number we can represent is approximately 1.8 times 10 to the power of 308. And that's the same between R and C++ because we're using same size doubles. So that's eval-CPP. Good for litmus tests, good for quick little expression checks, you know, is this valid, you know, can I find this identifier, sort of things like that. And you can augment it with some things too, and I get to that as well. CPP function we had seen in its use without arguments. First, without additional arguments. Standard use is you supply a string. That string shall be a valid C++ function. Required header lines are put around it. The try-catch business, everything that I mentioned sort of gets put around it too. There's actually the function will get called by another function. You can see all that if you turn verbose on. There's extension mechanism. We have so-called plugins, so you can turn on C++ 11. Then, for example, you can make use of features in C++ 11 such as auto-deduction of type. Here, the compiler will now know I'm assigning 10 to x. That means that x will be integer. Had I assigned 10.0 to x, x would be one of float and double, and actually probably double. I don't know. It will be written somewhere. We have other plugins, other language standards. You can turn OpenMP on and other things. So that's quite useful. And the way CPP function works and what we've seen is that the identifier embedded in the code that you submit gets used as the identifier for the calling function. So, but that's otherwise similar to what we've done with CumSum in these examples when we set them up. Finally, the most powerful of the 3, and something that you may be using a lot, but that you shouldn't use all the time. Just because this is good, don't stop before writing packages. I think we'll barely get to that today, but writing packages with Rcpp is also really, really simple. And do that because it has advantages. Just discussed in the break with someone other issues that this thing may have. But source-CPP basically compiles you on the fly from a single file. That is a mechanism to get more functions at once than you would get with CPP function because you get every function exported that has this exports tag. Similar to the plugins that we saw with CPP function, you can also put depends in to point to other header files, Amadio, Eigen, GSL, BH, you name it, stan headers, whatever you may need. And you can turn also conditional behavior on. Different C++ standards with or without OpenMP and sort of things like that. So that's source CPP, and that I still needed to do. So gallery, CumSum we'd seen, subsetting we had just done, and then the next thing is boost. Boost is a big deal. So first off, sort of definition. Boost here doesn't mean boosting as it does in machine learning. It's a different boost. Boost is something I think almost as old as R core. It's 20 plus years. It is, to my knowledge, the first serious program collection with peer review on the internet. So it's a super highly regarded collection of C++ routines, and it's a hodgepodge. It's 60 my dead server or my replacement server, and it's wrong mail name. Apologies for that. Hopefully this will be quiet now. So it spans a lot of different things. The first example that I'm showing here is from math extensions. There's graph theory in it. We have a package on CRAN on our bioconductor called RBGL, R-Boost Graph Library. So for minimal spanning trees and the other math algorithms that you do on graph as a data structure, that had always used Boost Graph. What else is it? There's a lot of things there. Boost had introduced a lot of things to C++ in really wide usage that is by now in the standards. Smart pointers, sort of things like that now are common, weren't when this started in 2000 or before 2000. So it's good. Usage, thanks to the deployment of header libraries, is really simple. When I gave the really brief intro with QNorm, that when you write a C++ program and you extend it with other facilities, you will always have to point to a header to define the functions that you use, and you may have to use linking. In that particular example, we used an older school C library that may come as a byproduct of your R build and has R functionality. A much more convenient way of supplying extra functionality is via headers. Then you only point to the header files, they get included, and you don't have to deal with the linking. That's the case for Boost. So all that we're doing here is, at one point in the file that we're sourcing, when we're using source.cpp, we say, hey, R, listen to Rcpp, and let it tell you that the BH package should be deployed. The general trick is when you build an R package and you create a directory inst includes, then you can point to this include directory of that package from the build of other packages via the linking to directive in the package. And depends basically does the same thing. It now tells the compiler, for what we're building now, we need facilities from a different package, and that is BH. BH is an absolute beast. You may have seen this when you installed another package. Many of them use it now because there's a lot of good stuff in there. Sort of token example is dplyr. If you do install.package dplyr, and you haven't had dplyr on your machine, it will install Boost. It's 15 megabytes compressed, it's over 100 megabytes uncompressed, and you don't really need it unless you compile against it. So that's a bit of I find of a sore spot in the R package system, because it's really a build time dependency, not a runtime dependency, but I digress. Boost Mask then has a lot of good functions. Here, to keep the slide simple, I just use two really simple ones: greatest common denominator and least common multiple. It's something that we don't have in the Mask standard library, that I think we don't have in base R. I think there's other CRAN packages by now, of course, that do it, but if you needed that, it's as simple as a simple function call, because you need Boost, Math, and then GCD. And we compile this through, and then you call it with, I don't know, 15 and 45, so then it'll probably tell you that it's 5. And likewise for the LCM. Many of them there. Documentation takes a bit of getting used to, because it's advanced C++, so it's not the most user-friendly, I find, but you generally end up finding what you need. This one's useful if you programmed for a while in languages other than R, because in R we can always do s dot type that I want to convert to, and mostly it just sort of works. Converting from strings to numbers, from numbers to strings, can be a little complicated. Boost has a very powerful library called lexical cast that actually does it both ways. Here I'm just showing one. So we're going in, and here I'm using a string vector the way it would expect it. Also the interface, Rcpp takes care of that. I could say here Rcpp colon character vector, or I could say in C++, Rcpp numeric vector, and I could say here Rcpp character vector, but vector of string is equivalent. The translations happen. I do the same thing here. I come in with a vector v, and its size, so it's all strings. I want to turn them all into doubles, and then I just loop over all of those. And I'm doing an explicit try catch here, because when this thing has a conversion it can't do, I think the error condition is an exception, which is why we have to do this. And in this particular case, we want, because we have a numeric vector, we just want to bring it back as an NA. R has facility to express the state of, you know, I don't know. So we do that. And one of the ways of doing that is assigning the C constants NR real to the position in there. And an example of using that would be calling it with a vector of 1.23, so a floating point number gets faithfully translated into 1.23. A shorthand for a floating point number also gets read properly. 0.4 becomes 040. An int gets read as 1,000. Text gets returned as a nar because that doesn't convert. 42 works. And of course, there's no magic here. This is not Maple or Mathematica. It doesn't do symbolic. Oh man. Computing. Yes. Penance. So pi over 4 does not get resolved magically. But that's, again, sort of just cost of a single header here. And I'm doing 2 using expressions here, meaning that I don't need to prefix this when I call that guy here. If I didn't have those lines here, I would have to prefix it. Yeah, would have to use that. So that just makes these 2 identifiers known for the compilation unit for the file. Here's one that I used years ago. That's a bit closer, sort of to my work. We sometimes need to know when certain financial settlements days are, and there's a convention that you need the 3rd Wednesdays in months, and this just shows how you get calendaring functionality out of C++ for free with the really nice use of enumerated constants. So nth day of the week in months, it's super verbose, almost Java style, and then : 3rd identifies the 3rd week in the month. Uppercase Wednesday is actually, after we included this header, a day of the week constant, and this one just gets us the nth day of the week of the month by saying we want the 3rd week, and in that week the Wednesday given this month. We then translate it into a date by also giving a year and translating that into a YMD thing so that we can pick up the components we need to return an RDate object via Rcpp. So quick illustration that a different library that's useful is boost datetime, which I use in a few packages. Another thing that was handy in the pre-C++ 11 days, if you want to enumerate over a vector in a sort of a more functional programming form, you can do that with the for each idiom. It's actually a macro here that gets shipped by Boost as all uppercase boost underscore for each. And I find sort of old, too many years programming C, all uppercase, I find a little sort of loud and offensive. So here I kind of just said, let lowercase for each be the same as boost for each with the preprocessor directive. So that's sort of tucked away, and then I can just say for each here. And this takes the vector x and accesses each element in x in a way that's bidirectional, passed by reference, so I can assign the value back. And when we're saying let element be the product of element, and with that we have a squaring function by traversing each element. I think we've seen something similar earlier with STL transform. This is now a sort of a lighter weight way of doing it with Boost. Next is an example of Boost with more than headers. So there's more stuff in there. So for example, Boost Datetime has formatting and parsing functionality, but if you want those, you need to link against it. Because we generally get dates passed from R and can print dates well with R, we don't need this. So in the uses that I had for Boost Datetime, I basically use the header file entry that declares just the types, the functionality that can be provided without linking. This now is a counterexample. Regular expression parsing is so deep into text processing that they cannot deliver this functionality in headers alone, so there's a little bit of linking involved. And possibly the simplest way to, in the R build system, have something link against the library is by just saying, let the environment variable packages libs that R command build, R command shlib, R command install, listen to, be -l boost regex. This works on a machine such as this one, where boost is part of the system build and is found in default library directions. That would be the case for most of us. I don't own a Mac, but I'm fairly certain that if you get boost from brew or other standard mechanisms, it also comes in a place where you don't have to -A say where the file is. Windows, sadly, does not possess the notion of a default library directory, so on Windows you probably need to have -l and then a -L supplying the directory. What we're doing here then is using boost regex, which uses a particular regex grammar, which is a little bit different of what we're using in R, but it's still digestible. It just basically means \d is a digit, so it means we want exactly 4 digits followed by either a hyphen or a space, all that grouped as a token. GSUB does the same thing 3 times, and then followed by 4 digits, meaning we have a total of 4 chunks, each being 4 digits, and they may be separated by hyphens or spaces. And that regex then can get matched, and each of these match produces a true/false. And then we can classify a vector of incoming strings of, say, candidate credit card numbers, and we get a vector of logical spec whether they pass or fail. This doesn't yet do really any semantic checking because the first 4 digits tell you whether it's Visa or MasterCard or what have you. But if we let this run, it shows us, for example, that a suite of 16 digits without spaces in them gives a false, that a suite where any one of the blocks only has 3 digits gets a false, and so on. That's the example on the gallery page. X pointer. So that's a bit more advanced. So if this is sort of your first day and first ever exposure to Rcpp, don't let your head spin. This is sort of the C++ equivalent of what we've done with the with passing a function down to an R function down to C++. The motivation basically is to overcome this problem that function calling is really expensive, but sometimes we need to do it over and over. We may want to do an optimization of an objective function we need to call with every candidate parameter vector. We may need to do, ML estimation, which is repeating. We may need to go to a sampler or sort of something. So we want to be able to have the freedom of switching between different functions, but we want these functions to be compiled. That's basically the setup. This is a working example. Again, it's on the gallery page with that URL following rcpp.gallery.org. And the 2 demos that I have here do Armadillo, which I think I'll get to in a bit. And they just send in a vector and return a vector. And we have a function fun1 that does not much. If the vector comes in, it returns the sum of the vector with itself. So basically, it doubles the vector, returns the sum of the vector with itself. And the second function, just to be different, takes a vector and scales it up by 10. So that when we print the function invocation, we clearly know which one got called. This could be more complicated. There's no loss of generality here. We could have a vector as well as a parameter vector, or other conditioning things to express state, but here it's really simple, and we opened up the ARMA and the Rcpp namespace because VEC is not in Rcpp, it comes from ARMA, so this is not clashing. How do we use something like this? So, well, we build ourselves a helper function that, given the value of a string from the user, the selection saying I want function 1 or want function 2, tests either function 1 or function 2, returns a the compiled function from the previous page properly wrapped so that we can ship it to R. And properly wrapped means we have to stick it into an XPTR, X pointer. That's the Rcpp type corresponding to the X pointer S expression thing that R itself has, that it uses to, you know, talk to databases, external memory, sort of things like that. It's a common paradigm. We need a type def here, sort of, so we can say we want an X pointer of a function pointer of this type, and that just means a constant vector goes in and a vector comes out, and we refer to that here as a function pointer to our function type for this exercise. So, and we create that thing by returning this cast to X pointer or function pointer by creating a new one of these with the address of either function 1 or function 2. That's sort of basically just getting hold of a function at the C++ level, how we would in R when we can assign a particular function to another identifier, and then, you know, then we have the function twice. So it's just basically provide the function to this other thing to make it shippable. And in case we were called with a third argument that's not suitable, we're creating a proper error condition by instantiating this with the nil which will lead to a well-called error, because that's not a valid function pointer. So that was the creator. This basically is, if you wish, the consumer. Here we're just saying, take this vector x. It would be good morning for me in Chicago now. We're passing the function pointer here as here I made it an S expression. I could have stuck that one in there directly as well. So here it's a two-step. I take the S expression, I instantiate an object of the X pointer of this type of the function pointer that I'm working with here, vector in, vector out. Now I have this in xpfun. I'm dereferencing the function pointer. That's just the way it goes. We have to do that extra step. So by taking value of this, now I have the function pointer in fun. And after those two lines, now I can get to work. For a given vector with a payload, you know, 1 to 10, 1 to a million, I'm now evaluating this as that function. And I'm storing the result, because the functions were set up to do an operation on a vector, either summing it up, either doubling it up, or scaling it by 10 and returning it, and I'm bringing this back. So this, again, no R code in there. This will all work at sort of lightning compiled speed. And putting this all together, usage at the R level then, for example, would be this. We have this R level callable function that creates the function pointer object. Given the switcher string that we put in, we said either fun1 or fun2 or error condition. That now gets assigned to a thing fun at the R level. It's a function pointer. It's a function pointer expressed as an external pointer object, which is a valid R object, which we can pass back and forth. And here it's the same thing to how we passed R functions down earlier, but now it's all compiled stuff. So it's all cool. And now I can call it with 1 to 4. And if I do it this way, I get, you know, 2 to 8 back. If I called it with the other one, I would get 10 to 40 back. And that works really, really well. We cooked this up and made it work for a toy package that I have, where I was interested in taking a C-level package from a bunch of friends that's moderately widely used. It's DE-optim. It allows you to optimize any odd function without supplying gradients or even Hessians, because it solves it by sort of a variant related to genetic algorithms, differential evolution. And that was a few years ago, and I was just curious if I could make it better. It was in sort of in early days. I think their main code is sort of 700 lines, and because it's C code, you know, and if you do an operation on a vector, you need to be explicit on the loops and sort of stuff like that. And here I have the vectorized. So I got the 700 lines down to 400 lines, and then I was nominally faster for a short bit, but that was just a side effect of me doing a code review. and the changes that I suggested, they then put back in. So then we were sort of the same, and and then I had to, of course, find another reason to snark at them. So now I can do this, because with Rcpp DE, you can optimize over compiled versions of a function. And if you've ever worked with optimization, there's sort of standard, banana function, Rosenbrock function, whatever. And with that, I can now be much faster than they, because the function that you're optimizing over can be supplied as C++ code. So it's a pretty powerful mechanism. And a friend once asked on this on Stack Overflow, there's an answer hiding somewhere that walks through the same thing in the context or wherever someone needs a gradient. So basically, just know that it's there. You can get your you can write solutions in C++ that do iterative things, and you can leave it so general that the users of your package can give you functions that you iterate over, do your actual work, and have those supplied as C++ functions if the need arises. So that's kind of neat. This now is back to the plugins. Oh yeah, that's right. Plugins, I said at some point. Hold on, there's something I should go back to when we went here. I meant to stop at that when we sort of saw CPP, right? We'd seen that we have things like the plugins and the depends for the other stuff where were we with Boost? When you have a depends here, those are all the things that you do with plugins. With source CPP, when you're building a package, you're declaring that either from the description file or the source makefast. So that's important too. But plugins are good because you have to apply the plugins, and then they get used either way. So this is how we implement the C++ plugin for our versions since 3+1, 3+1 or greater. We can just assign use CXX1X to yes, because R now knows how to deal with that. And for older versions, we had to make a difference between C++11 or C++0X, because before that time, the C++ compiler in R tools was C++4.6, and it only recognized this and not that flag, so that's how you can do that. This is an example of how we're enabling the OpenMP plugin, and that's a typo. That shouldn't be OpenMP ++11, just OpenMP. You basically supply a flag for the compilation step and a flag for the linker step, and then everybody gets that, but it still has some performance issues on Windows, and it's still a headache on the Mac. Typical use case of what one can do with C++11. So the auto thing we'd seen. There's also other features. For example, curly brace initialization overcomes a shortcoming that the old C++ standard have. If you had a vector of strings and you wanted it to have 3 elements, in the old days you actually needed to assign the first value, second value, third value in explicit steps, because the compiler didn't recognize this. This was sort of clearly a shortcoming, so the standards committee proposed that, it got accepted, and now if only we turn this on, which we can do sort of without really any cost or headache on CRAN packages too, because C++ is in all 3 build streams, Mac OS, Windows, Linux. Then we have the curlies. The next one is, I thought, did I have not the, okay, now 1 or 2 more. For each here is, oh yeah, no, exactly. This is what I was expecting. That it's the range thing. So this is now equivalent to what we had done with boost for each. Now you don't even need boost for it. It's in the C++11 standard. If you have a vector, you can just say, and now it's even 4 rather than an added macro that gets resolved. So now it's straight there. That gives you all the elements from the vector. And a super popular idiom then is actually to combine this with auto, and then people say for auto variable out of collection or something to iterate over that may be the single most used feature of C++11 anywhere. And so this is just a simple prod function that loops over a vector and multiplies all elements through. This would be the same thing, just how we had CumSum done several times. So this now does it with hold on. Why did I do that? It's actually not the same, because this one returns an int. So that's prod, and this one transforms a vector, so this is cumulative prod. Oh yeah, sorry, we had something else now, the lambda function, sorry. The topic of this slide is this thing at the bottom. Lambda function is sort of C++ big talk, or sort of functional languages talk. So, people always mention that. And if you're an R user, you can basically just sort of politely nod and kind of say, yeah, sure, we had this for a decade or longer. It's basically when you do an L apply or an S apply, you're saying, given this thing that one can iterate over, a vector or a list, do this other thing and invoke a function. So you're supplying a function on the fly, sometimes just defining it by saying in R, function, and then curly's defining what it does of a single argument. This is the same thing. It gives us the ability to do really simple functions right in this spot, rather than having the longer, more elaborated struct or functor creation that was needed beforehand. We had that a while back on one of the slides, and I didn't stress that too much. So, but lambdas, how do they get created? The key that the compiler hones in on is the square brackets where the naming would be. It basically just is a placeholder for this function. It has no name. It's only known in this scope. Otherwise, it's like a function. It has an argument, and it does something, and the return is implicit. So given a scalar double x, it just returns x to the power of 2. And then this one runs over all elements of a vector and squares it. And then, similarly, you can also do, or a good illustration of OpenMP is a package from someone in Austria called Rcpp Progress. It gives you sort of a progress bar. If you have something that's a really, and again, this is from a gallery page that has a full example. If you have something that's moderately expensive, and this just computes the distribution function of the log norm over and over and over and over again for 2 loops with large arguments, then you may want to see how long that takes. Getting hold of OpenMP, which is a vendor-independent compiler extensions that all compilers have, from Visual Studio up to Clang and all the rest of it. Again, there's some incomprehensible headaches being created by Apple by not sort of shipping that, but if you know your Mac stuff, you know where to get workarounds, then you have that. The way that this works is that you give, similar to our RCPP tags, these are basically meta instructions that if you don't have OpenMP turned on during the compilations, they're just skipped. Nothing happens. Similarly here, this block gets executed if you're in an OpenMP compilation, which requires this -f OpenMP flag for compilation and linking you get as a side effect from the plugin. And if that's the case, then this guy, for a threads argument greater than 0, will tell the runtime to now run, please, with that many threads, and prints it to the console so that you get a visual. So on a I don't know, 16-core computer in your lab, you would then have this running on 16 thread. And what it does is that after a pragma, OpenMP run me in parallel a for loop, and this is just an internal thing about how it schedules thing. It will take this outer loop and figure out how to spread it over the different threads and do the right thing. That obviously requires sort of some care with the libraries in the middle. But there's plenty of tutorials and books on OpenMP. I just mentioned it here. We actually have something nicer eventually in RCPP parallel if we get to that. How do you use that? The file that we're sourcing had the plugin for turning this on. If we're doing it with an argument of, what was it, 0 or 1, just a single thread, the elapsed time is just about the same time as the load was on the computer. All these DL norms with the 2 loops for a large enough number take about 22 seconds. If, however, even on the 4-core laptop, I say 4 threads, then the total computation time goes from 22 seconds to 25 seconds, because the old saw and with parallel computing, you have some communication between the workers. But the benefit is that the elapsed time went from 22 down to 3. So it's it's sublinear, also not uncommon, but for a simple loop on a rich enough machine, you get a speed up. Remember also, this thing was only printed when we're in OpenMP mode, and That was yeah, and from there, if you're sort of into this stuff, but you want more things taken care of for you, JJ and Kevin brought a really nice package making use of something from Intel called the TBB, the threading building blocks. It's basically a higher level abstraction for this OpenMP business that knows how to do things better. It has a bunch of heuristics about how to chunk things properly and sort of just do it right in I was just about to say in the sense that sort of, you know, Atlas knew better how to do matrix algebra on your CPU, but Edges gets that by massive testing. Here it's a little bit different. So it's just encoded in the library. And again, it's a header library, so it's easy enough for us to use. It's on CRAN 2. A working example here is serial case would just be take a matrix, create a new matrix, and what we really want is from beginning of end to matrix with the result in out matrix mat. Do me a square root, colon, square root just means run the square root function from the global namespace, so that's the scalar function from the C library. So it really just goes over the matrix and does it element by element, which is something that we can parallelize. The way this works, the way this paradigm is implemented in Rcpp parallel is you need to have a struct derived from worker, which is the thing that comes from Rcpp parallel. You then need containers, things holding values that need to be types that are not R types. So this is important. We can't use Rcpp numeric matrix or numeric vector here, because if you have R types, and when something happens in a multi-threaded context, every now and then R may get woken up into a garbage collection. R intrinsically is single-threaded, will always remain single-threaded, and those garbage collection can wreak havoc with your parallel computation. So it's much better, and that's stressed at length in the documentation of Rcpp parallel, to use these ones. And then we just say this square root thing gets initialized with input and output matrix that come in. And the key that then happens is for all of these things that we sweep over the data, they operate from some begin element to some end element, and it will just know how to chunk these to run them in parallel. And here, what we want is just a really simple operation, so we can use standard library transforms from the beginning of the input block plus the current offset to the beginning of the input block plus the current offset, starting at the same beginning pointer of the output block. And that allows us to operate on the matrix in chunks. And in order to get that to work, we need only just one more thing. We just write ourselves an R-callable function, parallel matrix squaring. That provides the input matrix. This is the output matrix. We initialize that worker thing that you saw on the previous slide with the input matrix X, the output matrix, and all we then do is, dear library, please run us this thing in a for loop that is parallel for the outer extent 0 to length, and then TBB figures out how many chunks to have, I mean, sort of given your machine and your memory layout and how big the matrix is and whatever, and just do the work defined in square root from 0 to length. And you know, then it splits and, you know, does from here to half and the half again, maybe in half, or however it does that. And that, oops, no timing. But that's also from a gallery page. So if you run that on your box with OpenMP, that you see that it will end up a fair amount faster. Why don't we, for kicks, just load that files. Yep, so that's the original serial example. That's the parallel thing. We set up the worker. So if I just source this now, again, laptop is 4 cores, so we get, in this particular case, for a, there it is, I think that's 1,000 by 1,000 matrix, 100 times. The time goes down from 700 millis to 730 millis to 240, so about a factor of 3 on a 4-core machine. Sort of not bad. Short file, short compilation. Don't really need to install anything exotic because Rcpp parallel is on CRAN and works just like everything else. And that you can run on the machine or your machine at home, and that's all good. So with that, I have another large block where we may skip 1 or 2 sections, but hit on 1 or 2, because this is other than the gallery, the single best sort of use case for stuff for you to just peek of how do other people do that. I mean, this is, I sort of do the same all the time. I mean, CRAN is just fantastic. We have sort of 10,800 packages on there now, over 1,000 doing Rcpp. So if you wonder about, well, how do I link to this or that? Generally speaking, you can find someone having done something similar, and then you can just, copy their mode, because it's on CRAN, it gets tested, it still builds, does the right results, so it's great. Among these 1,000, the single biggest one might be Armadillo, so I talk a little about Armadillo. Another important one is Eigen, started by Doug Bates when he was still working on Rcpp. It goes into LME4, which is a core package. And it's also used by Stan and a couple of other things, so this is an alternative to that. They both pretty much do the same thing. And then, then we may skip the GSL. It's sort of also nice to know that that's out there, but it's getting a little dated. And what should be on the overview page but isn't is at the end I have some slides on MLPAC. And MLPAC was sort of my great hope for this year, that I would devote a hell of a lot of time to the Rcpp MLPAC 2 package, but that too much stuff going on that haven't made as much progress as we hoped. But we will end with some examples from MLPAC. And MLPAC actually builds on top of Armadillo, so the two are related. So this shall be our focus. So this is so old school. Actually, no, it's really good. But Conrad is sometimes so stubborn. He still distributes it on via SourceForge. He has finally switched to keeping his code actually on GitHub. He's a bit of a funny character because he deletes old branches all the time and old commits, so it's just how our core is quirky. He can be a little bit quirky, but this is really, really amazing work. He is by now on his 3rd license, so he's a little headstrong there as well, but they're super liberal. So if you want to embed it in a commercial product, you can. Of course, if you're linking to it from R, it's still a GPL composite, but anyway, you could use Armadillo just in and by itself. I do that too. Man, someone give me a new server or a new sysadmin, please. Something with my XSIM configuration. Oh, come on now. Maybe I should turn the internet off. That's sort of the bullet points. That's the copy of the bullet points. So it's linear algebra. It's he really set out to. He's in computer vision, where MATLAB is really popular, and he really set out to give an alternative, provide an alternative for people who are familiar with MATLAB, which is similar to R, but sort of not quite. But if you can read MATLAB code, if you have written MATLAB code, this should be super accessible. In float complex, as I said, template metaprogramming, so we get delayed evaluation, so things are good. And so this is sort of pure C++, so you can spec things in Armadillo. You can prototype and develop really well from R via Rcpp Armadillo, but then you can have Armadillo solutions that you can deploy outside of R. So we try that a little at work, so that's good. Yeah, again, sort of there's documentation. He has an older technical report. We once wrote a paper for CSDA, and in the newer Journal of Open Source Software, Conrad and Ryan of MLPAC have a short thing in there too. And yeah, Armadillo bubbles up into MLPAC. MLPAC then bubbles up to that JMLR publication. So template only builds, no linking. That was one of the first big success stories. We had this before we had BH. That's really good. Makes it easy to contribute. We have proper glue code, so most data types go in and out without any issues. He works on it a lot. He's threatening to work a bit more on something that's functionally equivalent. So if you can read Armadillo code, he's now building one that does the same on GPUs. That'll probably be pretty good too. But so far it's this, and he's been pretty relentless with updates. So I toggled it down a little and try to only update on CRAN every 2 months to not overwhelm them. How do we use it? We've seen some examples in parsing. It's really simple. From R, if we have matrices or vectors, they just become AMA matrices and vectors. So just sort of an existing proof example that doesn't do too much new. If you go in with a matrix that's symmetric, you get eigenvalues back really simple by calling IXSym for symmetric matrices. So if you construct yourself a trivial 1 minus 1 minus 1, 1, you get 0 and 2 back. And if you call the thing from R, you get the same thing back. That's a almost FAQ, because people do this sometimes and kind of then claim that 0, 2 is not the same as 2 and 0. That's not true, because eigen decompositions are not defined up to their ordering. It's just the values. So a vector or the ref of the vector are really the same thing here. It's sort of there's no clear definition whether you should start from large to small or small to large. That being said, I find this more intuitive than that, but per share. I mean, that's just how it comes. This example comes in the package generator that I should probably get to in a second, but just breaking out. Given a column vector, multiplying the column vector with its transpose, n by 1 times n gives us an n by n, so outer product. In a vector, out goes a matrix. Same n by 1. If I multiply transpose 1 by n with the n by 1, I get a 1 by 1. And this is a quick illustration of how you're reducing something where the templated expression is an Armadillo type. So matrix times vector, vector times vector, vector times matrix, matrix times vector, whichever. If it reduces to a scalar and you want to assign it to a scalar, that's not automatic. That's sort of a design preference. He wants you to invoke as scalar, but that's what we're doing here. So here we have a simple example of outer product, vector into matrix, inner product, vector into a scalar. And let me just actually do what I threatened. So, one thing that I didn't even get to, because we only have the 3 hours, is package creation. I used to always suggest that you do this. My new package. We have a helper function Rcpp package skeleton, and the idea was so good, and we used that so much for so many years, that there's also similar skeleton functions in both Armadillo and eigen. So for all of these, you can say name of the package, .package skeleton, and a package gets created in your current work directory. So with that, let me go to temp here on this cloud server. So now, yeah, sure. Helps to load a package when you want to call a function. So that's one, oh, come on. One way of doing it. So that's now there, and you can build it and check it and all the rest of it. But there's another way, and that's one of the minute differences between the dailies and the release version of RStudio. Though I've just been told by Tarif that this branch 1.1. something will be the release version sort of before the end of the summer. So you would always go in and say new projects, either picking existing directory or a new directory, and when you then said R package, you went in there, you had to do this. Toggle from package to package with Rcpp. But as you just saw, they made that one better at one point in the winter. So Rcpp is directly there, and so are Armadillo and eigen. And it's even better. We all, as package authors, can drop a properly formatted description file and a subdirectory of our package, and then this menu grows. It's a bit like the add-ins. But now, if we want Amadio, we just say this, and then we just say, you know, AMA demo package. And again, here I don't plan to, you know, keep this forever. So let me just say temp, and then it switches to that. Create project. And this, again, gives us the way that package creators should work, a package that you can build and load, and it works without any headaches. So you have something to start from, and I think all package generators have a hello world in there. Oh yeah, sure. Sorry, they're in the package, not the environment. So demo package. Oops. So there's a hello world in there, and then the file of which we just saw the beginning is inner product, outer product, and both products. So I can now say inner product and wait, I typed that wrong. That was, what was it again? My inner product or something, my bad. Then we need a P here. Oh, come on. Oh yeah, better. Voila. So, and now, you know, you have a package that's set up with all the pieces, so you could just drop your function in here and you know, then maybe delete this one, and you have a working package. So that's the generator business. And this is sort of 2/3 of that. The third function just below it then returns a list with both of these results, just to illustrate that we can also return, of course, Rcpp list objects from AMA arguments. Use case, so this was something that got me going a really long time ago, over about 10 years ago. Maybe 9, with really basic Rcpp, so actually, maybe even longer. I think I did that with the GSL, and then it turns out it didn't work so well. So I trained as an econometrician, and sort of a popular way to earn a PhD was that you took a method that somebody had worked on and published a paper and had asymptotics, and then you kind of said, yeah, this is all good and well, but we're not working with data sets that are of infinite size. We need to know how this stuff behaves on finite sizes, so you do simulation studies. These simulation studies then, if it's on tests, often look at size and power of tests, so you need not only beta hat, but you need this guy. And R has a really fast function for doing linear regression over and over and over, lm.fit, but lm.fit only gives you this guy. So reasonably well-known financial econometrician now at UCLA had a question on R help. Yeah, you know, I need to simulate or compute something over and over and over. How do I do this? This one's slow. So I set out and wrote the first one. Turns out that one was not so fast, and I've been coming back to that a couple of times. And it's a nice example how the features in the package changed and how the code in the package is now even more compact and better. And it gives us an opportunity also to look at sort of one way of implementing this. So this, forgetting the old one for the GSL that really sucked, this one was the first one in Rcpp Amadio. And this is how we used to do things 7 years ago. So our interfaces actually still had S expressions in there. I didn't even get to telling you what S expressions are. That's sort of just this thing how R internally at the C level represents the everything as an object. Everything that exists in R can be, and you know, interfaces with compiled code, can be expressed as an S expression. I mean, you know, promises, functions, environments, a vector, a matrix, you name it, and we then wrote function interfaces that way rather than the way we do it now. We always used to use the same stanza, embedding the entire core of the function in a try block with sort of repeated line noise of the catch phrase that we need all the time, but that gives me a chance to show you something that we get for free now. This thing that when I stuck the character vector into CumSum, this is basically what happens. An exception is caught when is thrown when the object that cannot work gets instantiated. It says cannot do. We land over here. The exception is inherited from a standard exception. So this catch condition is true. And then we just have a helper function that takes the text of the expression, turns it into an R error message, and sends it back to R, and we're back at the R prompt. But that's a bit too much. Likewise, what we did here at the top was more work. We came in with one type from R. We made it one from Rcpp, and then we took the Rcpp one and stuck it into ARMA, because that was the only way to do it really fast. ARMA has a constructor where we basically say we have an object, and its memory storage really begins here. That's where the iterator is. And as you may know, vectors and matrices in C-like languages always stored in a contiguous block, right? Which is why we sometimes have problems with, well, I have so much free RAM left, but I can't allocate the new thing because you need all that size in one chunk. And a matrix really is a vector. It's n times k elements. You just need to know what the extent is. A 50 times 2 is different from a 2 by 50, even though they both have 100 elements. So you have to pass that on. Matrices are vectors with dimension. And lastly, false, meaning don't copy, be efficient. That's a trick that we can do here to be quicker, less overhead, efficient, but it takes basically 5 extra lines to come in with a matrix and a vector. And now we don't need to do that anymore. The actual work of doing a linear model with ARMA is great. This is why we did this. In the MATLAB world, you solve the regression equation by calling solve. Your initial static structure may have once explained to you why you shouldn't compute beta hat as x prime x minus 1 x. There's potential numerical instability there. If you're going through solve, you get decompositions that are preferable to outright multiplication. So little sort of standard stuff. That's what everybody says how you should do it, and that's how we do that. And you get residuals as the difference between x times the coefficients, the fitted ones, and the original data. And we then get the scaling factor by the inner product of, this is basically sum of squared scaled by degrees of freedom. And we get the diagonal of the covariance matrix by multiplying out trans x by x, inverting and extracting that. And with that, we have coefficients. We have the desired standard errors that were the whole reason to get into this. And because it's so cheap, we also ship out n minus k as the degrees of freedom. A newer version than a couple of years later was this. Now we have better converters. We basically just say, come in with a vector and a matrix, and then we just once still do this instantiation of the Armadillo stuff from there. So Rcpp interface from 5 lines down to 3 lines. The rest is still the same. And then 4 years ago, I think Romain went to work once more and made this cleverer still. So now we're actually coming in with ARMA types. We're doing what looks normal to a C++ programmer, that we're passing it as const with the reference basically saying x and y will not get modified. By reference means don't pass them as copies. Now we have them, and the rest of the code is just no more hand holding. It's straight there, and that's pretty good. There's a benchmark in the this just describes the whole thing again, what we're doing there with instantiation, and there's an example that still ships with a package that goes over a variety of these implementations. Constref is the current one. This was the early one with 2 cars. This was the earliest starting from an SEXP. They're all pretty similar. LMFit is a little slower on this example, which is a token example. It's the trees data set fitting volume as a function, log volume as a function of log height. and or girth. I think in the original example only on height. Now this one's then interesting. So we basically get all of this done, 5,000 replications of this really small regressions in somewhere between 250 and 270 milliseconds. Ask function takes 400. One of our other functions, I've forgotten what this one does, is about there. But then I had this for a couple of years, and then I felt a little sort of incomplete because I had a regression function there. The regression function didn't work with the formula interface. It always requires the more bare bones, here's a matrix, here's a vector. I think Glimnant still does the same, and I kind of thought, well, it's more R-ish if I have a formula. Turns out that deep parsing a formula and mapping it and getting your model matrix out is just about the most expensive thing ever compared to all the rest that is a regression, because a regression is nothing, right? I mean, we're projecting a matrix out for fitting. So all of these, including R's, are basically equivalent, no time, and even if you use hours, so the stuff that I set out to do faster than LM, by the time I have the formula deparsed, I'm 30 times slower, and worst of all, I'm basically indistinguishable from calling LM directly, which gives you so much more back. This one's reduced. So keep that in mind. You can very well spend a lot of time to get stuff fast, and then just falling into a particular usage pattern that takes that back. So always measure, always profile. This is the same thing now, just without the two formula ones, to see the difference between these two a bit more with a factor of 10 in here. And basically, that's just how they get invoked. And this, I think, for all intents and purposes, is just measurement noise. I mean, on the previous slide, the ordering was slightly different. Let me essentially skip this. This is another ARMA example, generating a vector autoregression, something that doesn't vectorize. When we do this in R, it looks like this. We create, it's vector autoregression, so 10,000 elements but 2 columns, so 5,000 each. This is the error terms. This is the transition matrix, how the, for row I, elements 1 and 2 of the columns interact. So it's 1/2 on the diagonal, 1/10 on the off diagonal. Each row then is coefficients times previous row plus error terms of that row. We can do that in R. We can do the same thing in C++. Each row is, the current row is the previous row multiplied the coefficients times the error term. I was minorly inconsistent that I had the coef on the left and the coef on the right, but it's just row times vector, so outcomes a row vector no matter what. And if you do that, you get a just by replacing the looping, sort of nothing else. We had amortized the random number draws by calling that first, so that one's taken care of, and you get about a factor of 50 on this type of hardware. Oddly enough, with the same type of processor, these numbers still differ between operating systems. So same example on a Mac. Maybe 40 or maybe 70 or something like that. It's a bit funny. There are other things happening. This one I basically won't get to either. This was an example I set up years ago for the piece that Conrad and I put into CSDA. I basically wanted to start with an actual MATLAB example to bring home this point that Amadeo is really good at converting MATLAB. So it's a simplest-ish Kalman filter, sort of estimating a movement on thing. I'm just going to flip over it. They have it on the MathWorks website to show how to do it with Max, the MATLAB compilation, to be much faster, and then of course ours is much faster still, and then I'm comparing one implementation another. It's in the package too, and that was basically sort of the end result, because this is our R plot of the same movement of the observed thing in and the estimate, the Kalman estimate from the observed trajectory of the object that the camera is on, or whatever we're having here. One last one from Amadeo. So something that's there in somewhat rudimentary form is being worked on this summer by a really motivated Google Summer of Code student is support for sparse matrices. So here is a really initial example, fully R. You take the matrix library, you define some I, j position and x values and created a sparse matrix. Then that sparse matrix comes back this, positions, I, j values, and creates a DGC. Again, we came in I, j, and c, I, j, and x. But if you look at the structure of the matrix, that's just the trouble with sparse matrices. And IJX actually internally becomes an IPX, and the indices is slightly different, so it's a bit hairy, and you have to get that right. But we have some things some initial things I put into Amadeo reasonably poorly, where you can do the same thing, sort of given IP and X, you can also set up one in Amadeo, and then it's the same matrix, it just gets printed the same way. There will be much, much more, not too soon, it's all already on GitHub, but in a different repo. And with that, MLPack. I think I picked up a T-shirt last year from Cloudera that said sort of data is the new bacon, because they wanted to sell you, Hadoop or Spark stuff. So we could now say that ML is the new bacon, because people it's just about as bad as CrossFit. Once people start about ML, they just don't stop. So I figured that's what I had to do too to fill the room, right? So I got to talk about Rcpp ending up in ML. But sort of kidding aside, there are at least 3 decent libraries. So Shark is one that I think started somewhere at a German university, I've forgotten where, and one of the people driving that now has a position, I think it's in Copenhagen, so I think it's there. And a friend of mine and I once looked at that, but didn't have enough free time to sort of work with that. So that's not bad, but that was years ago, and then a little later I started looking at MLPack and always liked that because of the Amadeo thing. dlib is another one I think that also comes from a vision focus, so they're all there. They're on CRAN, you can study them. Just how I like Amadeo a lot and use that more than Eigen. I'll focus now on MLPack, but I just should mention that there are at least these 3 and more. So what's MLPack? It's the work of Ryan Curtin and a really large number of other students while he was a doctoral student at Georgia Tech. He's now a researcher at Symantec, I think, Symantec, looking at viruses for computers and what have you, where automated detection, ML stuff, of course, is helpful. It's based around Amadeo, so Ryan has contributed quite a few things back to Amadeo, and it's easy enough to use. I just like working with it. And KK, who's an Rcpp contributor too, and committer. KK is the one who, as a Google Summer of Code student a couple of years ago, changed everything from len T vector types to xlen when R allowed larger lengths vectors. So we have that here now too. And he had once built an Rcpp LM pack that we call V1. It's on CRAN. It's good. It works. Everything's fine. But it's the old version of MLPack. So what MLPack has done is, that MLPack 1, now that at version 2 dot something or other. And one of the extensions was that they allowed serialization of an optimization estimation run. You can snapshot at any one point in time, dump it to disk, and then resume it. Now, this is MLPack, and their normal mode of distribution is small C++ binaries. You write a program, you build, and you have something small that you can execute. So they just link against Boost. That is a bit of a build problem for us because we generally don't have Boost. So we have an Rcpp MLPack v2 in the repo, and I use that. And if you have a system where it's easy to get Boost built and these things, then sort of you're good. But it's still a bit more work, and we're trying to make that a little easier on Windows and Mac OS. It's all doable, but it's not so automatic that we can toss it to CRAN. So, but I think we have an rcppmlpack.org or whatever we call it, or rcppmlpack organization on GitHub where these repos are. So by all means, come and send us pull requests. So external library now, meaning occasional headaches. But if you work on an AWS instance or have access to Linux, at home or in your lab or whatever, it's really not so bad. That's a copy and paste from the website. There's a lot of algos in there, so it's pretty good. It's pretty comprehensive. Standard sort of battery of supervised and unsupervised methods. It has, I just played with that the other day. It has some Lasso code. You know, getting that stuff to work is sometimes hard because the Friedman code in GlimNet is a little difficult to use. It doesn't yet have the automated cross-validation, but I think Ryan told me that's one of the things that they're doing this year at Google Summer of Code. So many things are there. And how do you get them to use? It's pretty easy with what we've seen now. You know, write little functions with an export tag into which go Armadillo objects, outcome Rcpp Armadillo objects, and in between you just call MLPack. So here I have an Rcpp depends on MLPack. And this one now, again, that's sort of the thing. It needs to find headers and needs to link against a library. So this will not necessarily work for everybody. It will work on, it was one of the benefits of that cloud instance till we shut that down because RStudio is kindly paying for it. So you can run this now and modify it. And then simplest example to start with is just standard k-means. And if you don't say anything else and get the default arguments and just go in with a number of clusters, they get data, number of clusters assigned into assignments, and we're returning that. And this I didn't rerun, but just copied from the vignette. With the wine data set in R, this gives you about a 30-fold over the R k-means. So that's not bad. That was, I think, the original example in Rcpp MLPack 1 by KK. I put a few more in by now. So this, for example, is, I really like benchmarking things and getting baselines. So this is, again, the equivalent to FastLM. It just does a linear regression. And before you groan and kind of say, why linear regression again, it's a bit more general, so it allows you to ridge. If you set a lambda parameter different from 0. That works reasonably well. Thank you. I think that was on purpose. I think you wanted to see this on the screen, but that's all fine. Yep, Lasso, then same thing. Oh yeah, here's a running example. So I went back to the sort of trees example and then just compare whether the fitted values are the same as they are in LM, and in fact they are. This is then one up. Logistic, and here I use a slightly different usage pattern, more common with ML sort of practices. We go in with a training data set and their lingo, labels, basically the classification that we want to run the logistic on. And here we're using something that we've now had for a year or two. We're allowing for optional types at the interface. So I did that with a by now former colleague at work, Rcpp nullable, instantiated as a numeric matrix. This gives us now the choice of submitting a matrix or not submitting a matrix, which we can do in R code all the time. But it's hard just to have a null pointer there and then instantiate it. But this one then works. And depending on whether we submit test data or not, we fit on the training data, and if the test data is there, is not null, then we also classify on the unseen test data and return the parameters as well as the results on the unseen data, whereas if we didn't supply it, then we just bring the parameters back. And that seems reasonable, so I may do a similar signature for the other ones too, so here as well, sort of to be seen. We have that here. There's a sorry, that should actually say logistic example regression because that's the same thing. So I work off examples that they have in the unit test because I can quickly check that I get the same thing. So there's a data set train set I put into the package based on theirs. The matrix is everything but the fifth column. They have, for reasons that someone will one day explain to me, the ML people all want what we have as long and skinny matrices transposed, and they're fat and shallow, so we have to do a T in here. Likewise, the excluded fifth column then is the labels that we want to fit on, and then I can call this matrix and labels, and I get the parameters back because null, right? I didn't supply the test data, whereas if I do the same thing on the test data set and I extract everything but the 5th column and then use my matrix, the labels on which it fits, and test data, then I get the same parameters back, but also a classification output on the results. This is a unit test example, so it's all very artisanal sort of, volumes. We're only classifying on sort of 7 data points, but the main point is I get the same classification back as they do. There's a lot of nearest neighbor methods in there. So this one uses a cover tree algorithm with an L2 metric. There's other things. I think we're almost there. That was that. And yeah, so I have a website. The slides will be there. You can email me. I prefer it usually when or it's better for everybody if the mailing list is used, or you sort of as a proxy sort of Stack Overflow, because then more eyes see it. Sometimes I just, I'm in a rush and I don't read your question carefully and I give you the wrong answer, and then it's just good when James is there or Keiki or someone else is there. And with that, I'm sort of almost at end, and we can do the all-important selfie, presenter selfie or two, because this is a big room. But otherwise, questions. I mean, if you have any, and I'm eventually done with this room, then maybe come up and use the mic, or I can sort of let me get out of the screen so you can see. Anybody has questions? Anything in particular worth repeating? Anything that I clearly said wrong and should correct right now, or later, or sort of follow-ups? Don't be shy. Ah, there's one, yes. Well, yeah, so two different questions. I'll repeat them. So the first one is, yeah, all good and well, but you didn't talk at all about distributed computing. And the funny bit is that when I started giving tutorials out at useR, that's actually what I talked about. And then it had, among other things, also a little bit of Rcpp in when it was much smaller. It works really well, because the way it works is once you have a package, you can put a package as a well-defined unit of computing for R. If you put the same packages on all your nodes, then you can use one of many computing distribution algorithms. I mean, Snow, for each, whatever, and just invoke things, because when Rcpp code accessible from R gets executed to R doesn't know anymore how we built it. It's just an R package that you have to get to your nodes. So it's no different. So if you master, and getting going with parallel computing isn't trivial, but if you're set up and have that working, then sort of you're good. And it's useful because you can prototype everything basically on your couch on Sunday afternoon on a single computer, take it to work as a package and put it on your 24 computers, and then they chuck away. So that works. And then the Spark example, yeah, that's just non-overlapping, right? I mean, the bit though is that and I haven't worked with it. I just heard from people using it. So Spark and all that comes with its own MLlib. And some R people have said it's sort of not so great. But then again, you could just horse race it, because MLPack is just a library. Spark is a mechanism to spread computation over different machines. So if you have a problem, you can run it with MLlib from Spark, and you can set it up with this. And then you can give a talk at next useR and tell us how it went. And chances may be that that MLPack is better, but I don't know. I don't know MLlib that much. We don't have Spark at work, so I don't work with that. But thank you. Good questions. Anybody else? Come a little closer. I heard the first half, but then it faded. So how is it different from the command line? I get to that, but then... Oh, yeah, libsvm, liblinear, that's a good question. I hadn't needed that, but they are already on CRAN, so other people have wrapped that. I haven't had to hit that from C++, so I haven't had to look into bindings, but that's no different from, you know, getting yourself access to other code that's there, where worst case you start by sort of copying it and building your own entry points where you can do much better and get functions exported from other packages. But that's that's standard R use. And then how is it different from other you know, it's just different. We work from the R prompt. And if I look at mlpack, everything that's shipped, the contrast isn't great, but this is sort of mlpack bin sort of underscore, hold on. You know, I could run sort of all of these, but then I would have to write myself helpers that dump data to a text file. They can read, get the results. But I mean, I could do that too. Sort of. I mean, if you're in a hurry and already have those, then you may as well use them. I mean, it calls the same code, right? So it's just I like to sort of bring them together that I have them in the R code. But it's functionally equivalent because you end up in the same library. Great questions. Anything more? So, we have a minute, right? I mean, it's just lunchtime. I mean, feel free to leave if you don't want to be here. Let me show you an example, if I still have a prompt here. So let's just do, oh yeah, very good. Call by value, call by reference. What the heck? So the very short answer is that, didn't have a slide for that either, every call that happens under the hood here happens through .call. It's the only interface we're using, and it's the only rich sort of good interface that R provides, and by good I mean modern. The old interface was .c, and .c only allowed you to basically have a numeric vector as a double star and a length of it. Not rich objects, functions, external pointers, you know, even lists at nested things. So I have that in the other presentation as a slightly longer thing. So I'm just setting up something really simple. I'm going in with a vector. I'm returning a vector. And in passing, I'm doing one thing. So, and I'm creating this vector this way to make sure that my vector is numeric. If I now call foo, foo was my function, right? Yes. And where did foo go? Oh, sorry. Yes. Sorry, I called the wrong library and I didn't recompile yet. This is what we meant. So now I have foo. Yes, I have a function foo. Here's my vector. I call foo. Foo just copies to another vector, and then in the incoming vector sets to 0. So look at this function signature. To a C programmer, we don't have any pointers there. We don't have any ampersands there. This looks like call by value. But it's not. Because everything that we get with .call and happens with the, hello, What did I just do? That's impressive. I don't return, sorry. That's what I get, so let's do this again, library. I was a bit impressed with myself that I managed to screw something this simple up so bad. But, you know, compiled code, so you can bring your session down. Not returning properly is one of the quickest ways. So numeric vector. So what happened? I had an outer vector 1, 2, 3. It's still up there. That outer vector didn't get altered. And that's actually, it's not quite the example that I wanted, but it's close enough. Then we come in and make that outer vector a newer vector y, and we're returning y. But the change that happens, only happens to x. What comes out still has the change. What happened here? Well, this thing is another S expression, and they share the same memory unless I request an explicit deep copy so that the two vectors y and x are separate in memory. When I do that and I assign to the other, the first is not affected. That didn't happen here. Now let me actually do the... let me do it this way. And that also works. So see that the vector, so now I just get foo2. And now I do foo2. I also get the same result back. But my outer vector also got changed. So even though, and that's a bit confusing for C purists, right? Even though we didn't in the function interface set, let x be a pointer. The sad thing is, or the good thing is, it always is a pointer because it's an SEXP, a pointer to the S expression, rather than schlepping the S expression over the heap each and every time. It's just a pointer, which has its advantages because if you have a matrix at 1,000,000 by 1,000,000 and you have enough RAM for that, you're not copying it through, you're just copying the pointer through. The downside of that is they're not shielded. But now comes the best one. So you've seen what I've done to vec, right? Now let me call ivec, set that one up, and make it 1, 2, 3. And if I now call foo2 on ivec, I also get 42, 2, and 3 back because inside the function it's clear cut, right? I'm assigning a value, you get it back. But what happened to ivec? Ivec is not changed. Why is that? What is different and what do we take away from that? ivec was an integer vector. In order to get into my foo or foo2 functions with numeric vectors, I need to create a new object. These cannot be the same. An int converted to a numeric actually is a new thing. Now the memory is separate, and with that I have no side effect. That is functionally equivalent, the same to doing this. I could arrange for that inside the function by calling clone. If I did that, now y is distinct from, let me restart with foo properly, and if I now call on this, not ivec, sorry, foo2 of vac, now the vector is unchanged because I arranged explicitly for them to be distinct. Otherwise, because it's effectively all call by pointers, so closer to reference, you got to be careful with side effects on things that come in. So that was a bit of a head stretcher for people the first time they've seen it. But it's par for the course. We'd rather not enforce hard cloning each and every time because then we would be closer to pure functions and never modify what comes in. But we would impose a copy operation each and every time, and we would slow everybody down. But that's sort of that's how we do things. That's how you live on the edge with that R stuff. We get pointers, so you have the ability to create yourselves headaches for the original data. Good question. Anything else? Otherwise, beer 30, we have lunch, and thank you all for coming and staying.